Welcome my friends, welcome to my next lecture. Now for this lecture, in fact I think I am in week 5. So in week 5 my plan is to talk about, in my last lecture I was discuss what is called Liouville's theorem. So now today I will start with just recall the Liouville's theorem once again, and then I'll discuss what is called applications of Liouville's theorem. That means many problems you can solve using Liouville's theorem. There are plenty of problems, so I'll discuss couple of those problems. There you can use Liouville's theorem very nicely to conclude your argument. And then as an applications of Liouville's theorem, then I can prove fundamental theorem of algebra. Then another beautiful theorem will come, what is called maximum modulus principle, and its consequences. You will see many nice kind of problem I will solve, I will discuss. And as an applications of maximum modulus principle, we will have Schwarz lemma, and at the end, if time permits, I will discuss what is called Morera's theorem. So that's kind of brief plan about week 5. So let me start with applications of Liouville's theorem. In other words, let me just recall Liouville's theorem once again, and then I will give some or discuss some kind of problems that you will be able to solve using Liouville's theorem. And you may expect that these sort of problems might be like I can give in exam as well. So that's what the learning outcome. So as I just said that these are the theorems, applications of Liouville's theorem. Then as an application we will have Gauss mean value theorem. Then I will talk about what is called maximum modulus theorem, maximum modulus principle, minimum modulus theorem. You will see. Then we will have Schwarz lemma and Morera's theorem. That's kind of brief plan of for week 5 lectures. Okay. So this is Liouville's theorem. I already discussed in my last lecture. Just to recall you, so Liouville is a French mathematician. So this is one of the beautiful theorem in complex analysis. According to me, it is one of my best theorem. Okay. So Liouville worked in many areas, different field of mathematics, including number theory, complex analysis, differential geometry, and topology. Okay, so he is mainly famous in complex analysis context is that Liouville's theorem. So if you recall, what is the statement of Liouville's theorem? So like if I have a bounded analytic entire functions, it has to be constant. So I gave an example in real analysis. There are plenty of nice functions like infinitely many times differentiable. It is also bounded, but you cannot say that your function is constant. Nice in that sense for real analysis. Like for example, sine function and cosine functions, they are nice means differentiable everywhere in the real line. It is infinitely many times differentiable. It is bounded, but the function is not constant. However, in complex case, the kind of if my function is nice means I am talking about it is entire functions, like it is analytic in the whole complex plane. And if I assume the fact that my function is bounded, then you do not have any other choice unless your function has to be constant. Okay, so that's the kind of theorem I already discussed, or kind of statement. So what is the meaning of entire functions? Just to recall, it is an analytic functions on the whole complex plane. That is the meaning of entire functions. Bounded functions means in fact you can think about in that way, it maps bounded set to bounded set, or you can say that yes, a function is said to be bounded if there exists a positive constant I will get m such that f of z is dominated by m for all z belongs to D. That is bounded. That means image of f should be a bounded set. Or yeah, so that's it. So image of set is bounded means what? You have to have a like some positive number m such that value of modulus of fz should be dominated by m for all z. Okay. So now I have entire functions, I have a bounded. The statement says that if f is entire and bounded on the complex plane C, then f has to be constant. So now the simple applications of Liouville's theorem. So like this kind of problem I already discussed, that sine function, cosine functions, you can prove that these are unbounded functions. Because one of the way I have proved the unboundedness of sine function and cosine functions, if you remember, I have the estimate. That means I have proved that sine z is dominated by something, and this is blow up infinity as something more, say mod y approaches to infinity. I think this should be sine hyperbolic y or something like that. Okay. So similarly for cos z. So in that way you can prove that your sine function and cosine function is unbounded, but instead of using this estimate, you just use Liouville's theorem to conclude that your sine function, cosine function, sine hyperbolic function, cosine hyperbolic functions, these are all unbounded functions. Why is that? If I assume that sine function, suppose prove as a method of contradictions. Suppose you have a sine functions f of z which is equal to sine z. So what kind of function it is? So it is an entire function, right? It is analytic everywhere in the complex plane. Assume that like you just prove the kind of argument via contradictions. Assume that it is bounded. That means this is dominated by M for all Z in C. Now your functions f is entire functions, it is bounded, that means it satisfies the statement of Liouville's theorem. So therefore what Liouville's theorem conclusion, your f has to be constant. But what is your functions? Fz is equal to sin z. In particular, if I take z is in real line, that means f of x is equal to sin x, and which is not a constant functions. So therefore you will arrive at a contradictions. And why you arrived at a contradictions? Because you started with a wrong assumption that your functions f of z is equal to sin z, it is bounded. So therefore this is wrong. So therefore your functions f of z is equal to sin z is an unbounded function. So this is a very simple application of Liouville's theorem. You can conclude that your sine function, cosine functions, sine hyperbolic and cosine hyperbolic, these are all unbounded functions. Then I also discussed the proof of it, very kind of straightforward proof. It says that, so I have to prove that my function has to be constant. That means I will show that derivative of my function is 0 on the whole complex plane. Then f has to be constant, right? So to do that, I started with a point z0, which is an arbitrary point in C. Now we will show that derivative at the point z0 is 0. Now it is given that my function is bounded, so therefore I will have the existence of one capital M such that this is true. Then what I have done is that considering a point z0, then I consider a circle of radius r centered at z0. That means this is the contour CR. What is my CR? CR is z minus z0 is equal to r. That means CR is the circle oriented positively, centered at z0, radius r. Now if I have that one, now my function is entire function. That means it is analytic everywhere. In particular, it is analytic inside the contour and on the contour. So therefore, if you remember or if you recall the Cauchy's estimate, you will have a Cauchy's estimate. Then you will conclude that the derivative, so I think Cauchy's estimate, we have nth derivative of z0, which is dominated by, I think if you remember, factorial n, m divided by, I think r to the power maybe n, I think something like that. You just check it, you just recall. So if I have a function f using the Cauchy's integral formula for nth derivative at a point, you will have this kind of estimate. Now if I take n is equal to 1, it will give you this kind of estimate. So therefore once I have that one, then using Cauchy's integral formula or using Cauchy's estimate, I can estimate my derivative of f at the point z0, which is dominated by m by r. What is m? M is the bound which is fixed. But what is my capital R? Capital R is the radius of my contour CR. But capital R is arbitrary. I can take any R. So now what I will do, this is dominated by m by r, whatever choices of r. So therefore the above inequality is true for every r positive. Then what I will do, I will take capital R approaches to infinity. That means you take bigger and bigger circle. Then what will happen, the right hand side approaches to 0 as capital R approaches to infinity, which will implies that derivative at the point z0 is 0. And since z0 is arbitrary, so therefore f prime z is 0 for all z, and therefore f is constant. Very simple applications of Cauchy's integral formula for nth derivative or Cauchy's estimate for nth derivatives for n is equal to 1. Okay. So therefore now at this the statement is clear, proof is clear. Okay. So now let me just see how I can use that theorem to solve many problems. So these are the problem. Couple of problems I have listed out. So similar kind of problem you can expect in your exam. Okay. So how to use Liouville's theorem to kind of conclude or to solve this kind of problems. Let me just discuss the first problem. What is that? What is my question? My question is that, does there exist a non-constant entire functions f such that e to the power f is bounded? Okay. Now, whenever I will ask this kind of question, then of course you can guess that I have to start with like negation kind of argument. That means, so method of contradiction somehow you have to kind of, that is the initial guess. That does not mean that whatever problem I will give, you have to always go through method of contradiction. No, that does not mean. But maybe this kind of problems, by your intuition, you can think about that. Okay, well, so the question is, does there exist a non-constant entire functions f such that e to the power f is bounded? So maybe you can just first kind of intuition should be, okay, let me just go with contradictions. That means assume that suppose there exists a non-constant entire functions f such that e to the power f is bounded, and using some kind of argument I will conclude that f is constant, which is a contradiction. So therefore my assumption is wrong. So therefore there does not exist any entire functions f such that e to the power f is bounded. So there are two ways, right? Either you have to prove it that there does not exist any entire functions f such that e to the f is bounded, or you can say that yes, look, this is the entire functions f and which satisfies these properties. So if you want to prove, like if you give a counter example, of course you are welcome, you can give it, or else you show that no, this is not the case, then it is better to go via method of contradictions. Assume that the whatever you are going to prove, suppose does there exist a non-constant entire function, and say suppose yes, there exists a non-constant entire function f having this kind of properties. Then try to prove some kind of contradictions. Here contradiction means you have to prove that f is constant, and there are many ways you can prove f is constant. This kind of problem I already discussed, like if I have entire functions, analytic functions which is taking purely real valued, purely imaginary valued, then this kind of functions constant you can already prove, you can already have it. So similarly, using Liouville's theorem and using method of contradictions, or you can have the explicit example of your functions, you will be able to tackle those kind of problems. For example, let me just talk about the first problem. What is my question? My question is, does there exist a non-constant entire function f such that e to the power f is bounded? You first go for method of contradiction. Yes, suppose yes, my answer is yes. Yes means yes, there exists a non-constant entire function. Yes, suppose there exists non-constant entire function f such that e to the power f is bounded. Suppose you assume it. So I will try to arrive at a contradictions. How do I do that? Okay. Now what is my f? F is an entire function, that means it is analytic everywhere in the complex plane. So you write f is equal to u plus iv, right? Fine, no issue. Acha. So let it be. Assumption, what is your assumption? There exists a non-constant entire function f such that e to the power f is bounded. But what is e to the power f? E to the power f is nothing but, look, so that means this is compositions of two functions. One is e to the power z composed with f. This is the functions I am talking about, okay. E to the power z of f. So that means these are composition functions. That means I am composing two entire functions. So f is an entire function, I assume, non-constant entire function. This is my entire functions. And exponential, you know, it is analytic everywhere in the complex plane. So this is entire functions. So if I write g of z, which is e to the power f of z, this is an entire functions. Okay. What I assume is that the entire function f is bounded. Now e to the power f is bounded means what? G is also bounded. Now g is an entire function, g is bounded. Now if I have an entire function which is bounded, then what Liouville's theorem says? G has to be constant. Therefore there exists a constant c1 belongs to C such that your g of z is exactly equal to c1 for all z in C, right? So therefore I can say that e to the power f of z, which is exactly equal to some c1. Okay, what I have to prove? Somehow I have to try to I'll try to arrive at a contradictions. Now e to the power f is constant. What does it mean? What does it mean, e to the power f? There are many ways you can prove that. This will imply that f has to be constant. You do not have any other choice. And why is that? Look, what you can do, so e to the power f is equal to c1, this is equations, and this is true for all z. And since you are dealing with both entire function, exponential function is entire, f is an entire, what you do, you take the derivative both side. E to the power f is equal to c1. If I take the derivative both side, then what will happen? E to the power f times derivative of f, right, by chain rule, right, and this is exactly equal to 0, right? So therefore what you will have? E to the power f times f prime z is equal to 0, and what it will imply? If I take the modulus both hand side, so e to the power f times modulus of f prime z, which is 0. But since f is a non-constant entire functions, so therefore this object e to the power f, which is always non-zero, right? So therefore this will implies your f prime z is 0. Now since f prime z is 0 and this is true for all z, so therefore you can say that f is constant. And since you arrive at a constant but you start with a non-constant entire function, so there is a contradiction. So therefore there does not exist any non-constant entire function f such that my functions e to the power f is bounded. So that's how you can use what is called Liouville's theorem. So first one is clear. Assume that yes, there exists a non-constant entire functions f such that my functions e to the power f is bounded. The only fact you have to somehow identify, yes, f is entire, exponential is an entire function, compositions of two entire function is an entire function. So therefore g, which is nothing but e to the power f, it is an entire function, and by hypothesis that e to the power f is bounded, bounded entire implies by Liouville theorem it is a constant function, e to the power f is constant, take the derivative both sides, assume the fact that e to the power f absolute is non-zero, then you conclude that derivative is 0 for all z and hence f is constant. Okay, what about the second one? Does there exist a non-constant entire function f such that real part of f is bounded? That is another nice function. How do you do that? Okay, so again as I said, so you just try to kind of go ahead with what is called method of contradictions. Well, at least for the second one also. Okay, second one also. So what will be your assumption? Assume that, suppose yes, this is the case. Suppose I assume that there exists an entire function such that what is called real part of f is bounded. Then you have to somehow try to give a contradictions. Okay. Okay. So same thing. How do you do that? Okay. Let me just check it. Okay. So second one. So first one is done. Second one. Second one is that, so assume that yes. So assume yes, there exists a non-constant entire function f such that real part of f is bounded. Okay. Now if f is equal to u plus iv, since f is entire I can write u plus iv. So what is real part of f? Real part of f is u. You have to arrive some kind of contradictions, and what contradiction? That means you just somehow you conclude that your f is constant. That means there does not exist any non-constant entire functions f such that real part of f is bounded. Okay, now how to handle that problem? So to handle that problem, somehow you have to guess it or you have to apply Liouville theorem. Now to apply Liouville theorem, you have to somehow in your hand you have to somehow produce like what is called entire functions and conclude that yes, this is bounded, then it is constant, then give some kind of argument. Okay. Now you see, I am assuming that yes, there exists a non-constant entire function f such that real part of is bounded. But then you have to apply Liouville theorem. Now you cannot apply Liouville theorem here, right? If f is an entire function, real part of f is bounded, but it could have that imaginary part could be unbounded, no? So therefore you cannot apply Liouville theorem on the functions f itself. Because f means what? You say that there exists a non-constant entire function f such that real part of is bounded. That you can have it, no? So that means you can assume that okay, real part could be bounded, but it might happen that imaginary part is unbounded. So therefore you cannot apply Liouville theorem on the functions f itself, because real part of f bounded will not imply that your function f is bounded. So instead of dealing with the functions f, you should deal with this kind of functions. G of z is equal to e to the power fz, like mean this kind of functions. Now look, so what is your function small f? Small f is a non-constant entire function, so therefore f is entire, exponential is an entire function, so e to the power f is an entire function, g is an entire function, perfectly alright. Then what I will do, then I can say that take the modulus of g of z. Okay, what is that? Modulus of g of z, that means modulus of e to the power f of z. What is that e to the power f? F is u plus iv, that means it should be e to the power I plus uv. And u and v are real valued, so if I take the absolute, then by complex number what will happen? So this should be e to the power u times e to the power iv. But v is real, so e to the power iv is 1, so therefore this should be exactly equal to e to the power u. So what we'll have, I'll have an entire function g such that modulus of g is exactly equal to your e to the power u, right? Or yeah, e to the power u, that's it. But what is u? U is nothing but the real part, and what is your assumption? Real part is bounded. So therefore you can say, so well, you can say that this is well, e to the power modulus of u, fine, perfectly all right. So yeah, okay. So therefore we can say that since real part of f is bounded, so therefore modulus of u, which is modulus of real part of f, is bounded. Let it be m for all z in C. Since u is bounded, so therefore e to the power u is also bounded, so therefore you can have less or equal to some n, and this is true for all z in C, correct? So therefore, instead of dealing with the functions f, now you deal with the function g, which is e to the power f, which is an entire function, and if I calculate the absolute of g, it turns out that it is exactly equal to e to the power u. Now your assumption is that u is bounded, which is real part of f. Now if u is bounded, so therefore e to the power u is also bounded, and this is bounded by say some constant n for all z. So now therefore you have a function g which is a bounded functions. Now g is an entire function which is bounded. So therefore what is Liouville theorem says? So therefore by Liouville theorem says that there exists a constant c2 in C such that g is constant. Now g is constant means what? E to the power f is constant, and that will imply f is constant, and which is a contradiction because I am starting with non-constant interval. Okay, so this is the nice applications of Liouville's theorem. So second one, you have to apply what is called the first one. So just look at the real part of f bounded with the fact that f is non-constant entire functions. You just cannot apply Liouville's theorem on the functions f itself. Rather, you just kind of take a modified function that is called g functions, which is e to the power f, and kind of conclude that yes, now the function g which satisfies all the hypotheses of Liouville's theorem. Now g is entire and absolute of g is bounded because of the fact that real part of f is bounded, then it implies that g is constant, therefore e to the power f is constant, will implies f is constant, small f is constant, which is a contradiction. What about the third one? Third one, same way. So there exists a non-constant entire function such that imaginary part of f is bounded. How do you prove it? Well, now this is similar kind of way, but this time you have to deal with a different way. See, what will be the modified functions? So you cannot apply your functions f or this called Liouville's theorem on functions f itself, because imaginary part could be bounded. It might happen the real part is unbounded, so it will have f is unbounded. So you cannot apply Liouville's theorem on f itself. So therefore you have to kind of deal with some auxiliary functions. Okay, and what is that functions? For second one, you will have gz is equal to e to the power f. If I take this one, then modulus of gz is turns out exactly equal to e to the power u, where u is the real part of f, and real part of f is bounded means e to the power u is bounded, that means modulus of gz is bounded. Now instead of real part, if I deal with imaginary part, then what function I should take? You can easily guess. Gz should be e to the power what? I times f. That's it. Instead of well, maybe you can say that minus I times f. Yes. Now again, f is an entire functions, minus I times f, this is a constant times f, this is also entire functions, exponential composition with exponential function, that is also entire function. So therefore g is entire. That is one fact. Now what is the modulus of gz? If I calculate the modulus of gz, then you will see, so if I calculate the modulus of gz, then what will happen? So this is modulus of e to the power minus f, which is modulus of minus I times u plus iv. Okay, then what is that? Absolute of e to the power minus iu times e to the power b. And what is that? This should be, this is 1. This is exactly equal to 1 because u is real valued. Okay, so and this is what? E to the power b. Now what is b? B is nothing but the imaginary part of f. So therefore now you have an entire function g whose absolute is e to the power v, which is imaginary part of f, which I assume that it is bounded. Suppose go for contradictions. So therefore v is bounded, but v means imaginary part of f is bounded. So therefore this is bounded by constant sum m naught. So therefore I have a function g which is entire, which is bounded. So therefore by Liouville's theorem there exists a constant c3 such that g of z is equal to c3. But what is g of z? G of z is equal to e to the power minus if, which is c3. Do the same conclusion, take the derivative both sides, you say that f is constant, and which is a contradiction because if I assume that there exist a non-constant functions. So therefore since it is a contradiction, so therefore there cannot exist any non-constant entire functions f such that my imaginary part of f is bounded. So these are the kind of nice problem you should try using what is called Liouville's theorem to give your argument or to solve problems, to give the justifications. So this is very nice. Okay, so these are the problem you should complete. Now what about the fourth one? The fourth one, what is that? Now does there exist a non-constant entire functions f such that f of x is bounded for all real x? Okay, so how you will proceed with that? Okay, so for example this one, how you will do that? Does there exist? So now you should not always think about that. Does there exist? If I use this kind of word, that means answer should be negative, and I have to say with a method of contradictions. No, it is not the case always. For example, does there exist? There is a non-constant entire function out of 3 above 3 1 always give a what is called negative. No, there does not exist any non-constant entire function which are having these properties and these properties. However, if I have the fourth one, maybe you can think about that all the 3s are negative answers, the fourth one also have a negative answer. Answer is no, fourth one has a positive answer. You see, does there exist a non-constant entire function f such that this is bounded for all? Answer is yes, there exist a functions, and you are already familiar with this kind of function. What kind of function? Does there exist a non-constant entire function f such that f of x is bounded? This one more extra is there. Answer is yes. Consider this function f of z is equal to sin z. This is the entire function, right? Sine function is the entire functions on the whole complex plane. Now if I take z is equal to real line, that means z is equal to x, then what it will give? F of x is equal to sin x, and sin x is bounded functions. So but yes, there exist a non-constant entire functions f fz is sin z, which is non-constant entire functions. If I restrict z on the real line, that means it becomes f of x is equal to sin x, and it is bounded, So therefore, if I give that kind of problem, like does that exist, by default you should not assume that your answer is always going to be negative. Now it might happen that answer is going to be positive. Okay, so just to kind of give a distinction between these three, I have given this kind of problem. What about the last one? This is another interesting problem. Does there exist a non-constant entire functions f such that modulus of fz is strictly greater than 1? Okay, this is another nice problem. There also you can see yes, no, there does not exist any non-constant entire functions which having this kind of properties. So maybe again you can go for method of contradictions. So assume that yes, suppose yes, there exists f which is non-constant and entire such that modulus of fz which is greater than 1, and this is true for all z in C, right? So now again, since I assume that method, I am going through method of contradiction, that means I have to apply Liouville's theorem. Liouville's theorem, that means I have to somehow find out functions, entire functions, and I have to somehow give some argument, say that yes, this is entire function, this is bounded, constant, and will arrive at a contradictions. Now just you cannot apply your Liouville's theorem, your entire functions f, because modulus of fz greater than 1, it might happen that it's taking larger and larger values as mod z approaches to infinity. So therefore you need to kind of get an auxiliary functions where you will apply your Liouville's theorem like you have done for this case and this case. So what you can do, by looking at these functions you can easily guess it, because you see what is the conditions. Condition is that absolute of f of z should be greater than 1, and this is true for all z. That means from the properties you can easily say that f of 0 cannot be 0, right? So that means z, if z is equal to 0, modulus of f0 is greater than 1, so f of 0 is non-zero, right? So that first assumption is that, oh okay, so therefore not only that you can say that f of z is non-zero for all z, that is also you can guess it, right? Because modulus of fz which is strictly greater than 1, so therefore fz is not vanishing on the whole complex plane. Now since fz is not vanishing on the whole complex plane, then you can automatically consider a new function which is gz, which is 1 by fz, right? That you can consider, because f is not vanishing on the full complex plane, so therefore 1 by f makes sense. Now what is given? Yes, there exists a non-constant entire functions. Now g function makes sense because f is non-vanishing on the whole complex plane. Now 1 by f, this is also entire functions. Why? Because quotients of two entire function is also entire functions, provided the denominator should be non-zero. Yes, f is non-zero entire functions. Numerator is 1 constant function, it is also entire functions. Quotients of two entire function, it is an entire functions. Therefore g is an entire function. So this is entire function. This is my auxiliary functions. Now just to show that whether with that assumption whether g is bounded or not, answer is yes. Why? Because modulus of gz, which is same as modulus of 1 by f of z, which is equal to 1 by mod of fz, but mod of fz is greater than 1, so 1 by mod of fz what? This is less than 1, and this is true for all z in C. So therefore this auxiliary function g, which is an entire function, which is bounded. So now I can apply what is called Liouville's theorem. So therefore by Liouville's theorem, g is constant sum C naught by Liouville's theorem. Correct? Because g is an entire function which is bounded by hypothesis, so therefore g is constant. Now g is constant means what? G is equal to 1 by f, so therefore f is 1 by C naught, and which is a constant function, and which is a contradiction because I am starting with a non-constant entire function. So this is another beautiful problem. Like using Liouville's theorem, you can say that there does not exist any non-constant entire functions f having the properties that modulus of fz is strictly greater than 1. Okay. So these are very few kind of problems I have discussed, but using Liouville's theorem there are plenty of problems are available. As you can see, you can consult with many books, and using Liouville's theorem you can conclude your argument. So I have done like very few. You should kind of consult with many books and the problems, and I hope you will be able to. These are the kind of ideas how to apply Liouville's theorem to solve some of the problems. Okay, so now this is all Liouville's theorem. Another applications of Liouville's theorem is that I will prove what is called fundamental theorem of algebra. That means if I have a polynomial, say complex polynomial of degree n, then I will show that it will have n many roots in the complex plane. So that means the complex plane is algebraically closed. Okay, so the fundamental theorem. If I take a polynomial of degree n with complex coefficients, so it will have n many roots. That means I can factorize my polynomial into n many factors. Well, root can be repeated, but that doesn't matter. So as long as I'm dealing with degree n, so I can have n many factors. I can factorize. Okay. So for that, so I need some properties of non-constant polynomials. Once I have that properties or the estimate, then you will see how I can apply Liouville theorem to conclude what is called fundamental theorem of algebra, or give a alternative proof of fundamental theorem of algebra using Liouville theorem. So for that I just need that theorem. Okay, what is that theorem? Maybe next class next lecture I'll like give a proof of it. When we start with the once again, let me just discuss the statement, then it will be clear. So what is that? So this is that's why I've written what is called, this is properties of non-constant polynomials. If I have a non-constant polynomial, then it will satisfy some kind of estimate. What is that? So it says that let P, which is a0 plus a1z plus a2z square up to nz to the power n. Suppose it is a polynomial of degree n greater or equal to 1. That means the corresponding coefficients of z to the n, which is non-zero. Then there exists a positive number r such that you will have this kind of estimate. That means modulus of pz should be greater or equal to half of modulus of n times mod z to the power n, and it is dominated by 3 by 2 times mod n times mod z to the power n. So therefore, in terms of the coefficients of the nth power of z, you will have this kind of estimate. Okay, and this is true for mod z greater than r. That means if you see, look at the complex plane. So if I have a complex plane, so that means suppose this is my r. Okay, so suppose this is mod z is exactly equal to r. So that means here mod z is greater than r. My functions, that means the polynomial, have this kind of estimate. It will have an upper bound, it will have a lower bound for mod z is greater than r. And you will see, using that estimate and using Liouville theorem, I will be able to prove what is called fundamental theorem of algebra. This will be an alternative proof, very beautiful proof. But before that, I need this kind of estimate. Okay. Anyhow, this is like purely algebraic. Okay. I have to somehow write my polynomial in such a way. And you have to just do some algebra with an appropriate modifications and appropriate estimate. And of course, you have to use what is called triangle inequality. You will be able to prove that one. Maybe in my next lecture, I will start with this proof of this theorem, and then I will prove what is called fundamental theorem of algebra using what is called Liouville theorem. So that is one of the nice applications. And then I'll go to what is called Schwarz lemma or maximum modulus principle. So there, of course, Schwarz lemma, I think, yeah, you can, okay, using maximum modulus principle, you will be able to prove Schwarz lemma. And maximum modulus principle also I'll state and I'll prove. Let me see whether whatever knowledge we have till now, whether we will be able to prove that maximum modulus theorem or principle in this week or not. Okay, so I think I should stop here. In my next lecture, I will start with the proof of this theorem, that means properties of non-constant polynomial, and later you will see how these properties along with Liouville theorem to conclude what is called fundamental theorem of algebra. I think I should stop here. Thank you. Next lecture I'll start with the proof of this theorem. Thank you.